So today what we're going to do is just going to review the relationship between dt, dt, and AT graphs. We've already done a little bit of that, but the main sort of new thing that you haven't done a lot of is creating VT graphs from DT graphs and DT graphs and VT graphs. You've done the first one, you've created VT graphs from DT graphs. We just did that was question number 4. We'll do a little bit more of that, and then we're going to go backwards. Okay, we're going to go backwards. It's, for those, anybody taking advanced math this year? Do we still teach that?
Yeah.
Are you taking? Okay. So when you get into the calculus stuff, when you start talking about derivatives and integrals, some of this will make a little bit more sense, and that will make a little bit of sense to you as well, if they tie in calculus with physics. And I don't know if they do. Who's teaching that, Peyton? Okay. I don't know if he teaches that or if he brings in physics. Right. I taught it a couple times too. It's good. Okay, so let's begin. So we're here on page 2.2, moving from one graph to another. Now, I could just say copy this out from the book, but that wouldn't be a lot of good, I don't think, right? What I basically did was I cut this off, and I want to go through it with you, and I want you to draw it, and I think by you drawing it, it'll start making some sense to you. Okay, and I will draw it as well. Okay, so you've got the first 2 columns there. So, if I have a DT graph, I'm going to just move this over a little bit here, yeah. And I should lock it in. Move this to a good spot and lock it in. Okay. So if I've got a DT graph, I'm stopped, right? My DT graph is there, right? The velocity time graph is right at 0, right? You can mark that at 0 if you want. Maybe put a 0 there. I don't know. Do they have that on the book? No, they don't, right? And this means that the velocity is 0. What is the acceleration? 0. Why is the acceleration 0? They're stopped, right? They're not changing speed. And the example, the picture, is the track and field person preparing to run. And they've got really long, crazy arms. See? This is always the fun part, me drawing. And you should draw that as well, because I want to come around and make fun of your drawing. Kind of looks like a gorilla getting ready to run, right? There? Okay, now the next one shows, there's 2 versions of stopped, isn't there? That's right. There's 2 versions of stopped. Now, okay, this is the part I don't like about the book. Where is this person stopped on, we'll just say they're on a number line. Where are they stopped?
Stop facing the positives.
Do they have to be facing the positives? I don't think so, right? I don't think so. All this means is that they are stopped. Where are they in relation to the origin, the start line? They're to the right of the start line, right? But do they have to be facing forward? I don't think so, right? It just says that they're stopped. Does it matter which way they're facing? Not if you're stopped, right?
But then what if they were facing forward and they wouldn't go forward, they go in a single line?
Are we now predicting the future? Why can't someone be stopped in the positive area and then start going negative? Why not, right? Who knows? This is constant velocity stopped as well, just stopped in a negative territory. Now they show it as, and I always have trouble drawing things the other way, so this I cheat and I do this. Oh no, don't do that. No. There. I'm not a cheater. Yeah, I know. We're just going the other way, right? And again, now where's the start line here? Where's the start line? Because they're stopped in negative territory, right? So shouldn't it just be like this? Right? To the left of the start line? Doesn't that make sense?
Yeah. The start line is like 0.
The start line is 0, correct. The origin. Do they necessarily have to be facing left? We sort of want them to be because we think they're going to be running left, but I don't think that's necessarily true. Okay, the next set is constant velocity. So the person is running with a constant velocity, and our dt graph starts at 0 and goes up, right, in a straight line, which means the velocity is flat line, right, and my velocity is constant, and my velocity is greater than 0. They show that like this. It's greater than 0, and it's constant. How do we know it's greater than 0? Two ways. Here the velocity is above 0. Here we see that the slope is positive. And my acceleration would be equal to 0. How do I know my acceleration is equal to 0? Constant velocity, and the slope of the VT graph is flat. Right. Yes, absolutely. Good question. She asked if the slope of the dt graph corresponds to the number that the VT graph is flat at, right? Right. So for in other words there, if the slope m is, say, equal to 3, then this value here would be 3, right? Is that what you're asking?
Yeah.
Okay.
Will it always be like that?
Yes, absolutely. The VT graph is a graph of the slope of the dt graph. It is, and that's where the calculus comes in play. Okay? Because calculus is all about slopes, right? We would say that v is the derivative of d. V is the derivative of d, and only people that are taking calculus might need to know that, right? Derivative, D-E-R-I-V-A-T-I-V-E. Huh? I don't know what that means. Oh. I have to use the word derivative in a function? The velocity time graph is the derivative of the displacement.
When should we ever use this in real life?
Well, if you're like a rocket scientist or something.
Where's your drawing?
Oh, I haven't done the drawing yet.
Please.
Yeah. Thanks, Diane. I gotta make myself some room here. I'm gonna put the 0 up there. Okay, yeah. I quite often have to sort of cheat by copying it right from the book. Okay, so they're running at a constant velocity. Wait. Hey, not bad, eh? Nothing like a skinny, bald, blue stick figure guy running. He has a transparent head. Okay, so constant velocity now moving to the left. Again, we're at 0. Let's assign the velocity or the slope to be -3 just for sake of argument, which means that this line is graphed at -3, and the velocity then is less than 0 because it's below 0, and the slope here is negative. And once again, the acceleration is 0, and the blue skinny stick figure man is traveling to the left. Now, is that true? Does he have to be going left? Oh, didn't copy it. Flip. I can't draw them running to the left for some reason. Does the stick figure guy have to be running to the left? Does he have to be?
Yeah.
No. What do you need to be running towards the origin?
Okay, let's go with Joey's thought for a second. Here is the origin, right? So where does he start running?
Away.
He starts running at the origin, and he's traveling negatively, right? So I mean, I guess you're going to draw the picture at the sort of at the end of this graph. He must have started at the origin, and does he have to be going left? Absolutely. Why? His velocity is negative. He must be traveling to the left. right? Negative. Right? Yes, must be. Okay, let's jump down to speeding up. Speeding up to the right. This is the displacement time graph. This is 0. Now, can we assign a slope to that? Can't. How come? It's changing. Like here, the slope was constant, right? Plus 3, minus 3, it's like a straight line. Here, it's a curvy line. The slope changes. It increases. So that's why the VT graph, which is a graph of the slope of the DT graph, the slope, the value of the V is doing what? Going up, rising, increasing. My velocity here is greater than 0. Why? Because it's above. But my acceleration is also 0. Or not, yeah, greater than 0, not equal to 0. Why is the acceleration greater than 0? It's speeding up, and the slope of this VT graph is a positive value, right? Whatever the slope here is, let's assign this slope here to be, just for fun, as much fun as a physics teacher can have. Let's assign the slope here to a plus 4. What would my acceleration then be? 4. And if I were to draw an acceleration time graph, what would it look like? It would be flat at 4. And guess what, Peyton and Chris? Acceleration is the derivative of the velocity. You want to draw jerk graphs?
Yeah.
Joey must have heard that talk about the jerk factor. The jerk factor is the thing that comes after acceleration. The jerk is the derivative of the acceleration. And so on down the line. Yeah. Do you want me to give you that quick calculus thing? No? Okay, so this time here, the stick figure person is accelerating. And let me see if I can draw this. Back leg extended, knee bent, back low, head attached to arm. Not bad. Not my best. They always have that long forearm for some reason. Oh, it's got. I should get Mr. Miller up here drawing for me. Oh. Oh, missing an arm. Oh well. Okay, now the next one here. What if I'm going the other direction? Speeding up but negative. Speeding up but negative. Is the slope here increasing? Is the number value increasing? Yes, because the slope here is 0 and it becomes more and more negative, like -1, then -2, -3. The number is going up. It's going up in a negative fashion, right? And the velocity is getting more and more and more negative. The velocity then is less than 0, negative, below. If I assign this slope of -4, then my acceleration is also less than 0, and my acceleration is -4.
So it's slowly increasing or decreasing.
Of the acceleration time graph? The acceleration time graph would be flat at a value of -4.
Okay, but for the first part, I was going down to 36.
Here you would say the velocity, I would say the velocity is increasing in a negative direction, to be clear, right? If you say decreasing, does that mean slowing down or does that mean going faster negatively? Kind of both, right? So I would have to say, especially if I'm explaining to kids, I would say that it's increasing in a negative direction. Am I good? Yeah? Okay, so let's see if I can flip this guy around. Draw in the missing arm. It's not the Paralympics. There we go. I guess it could be. There's nothing wrong with that. Where is the origin in these two cases here? Here they start at 0 and they're traveling positively, right? So behind there, and here he starts at 0 and moves left. So I'm going to move him and his arm over there. Still behind, exactly. Okay, slowing down. Slowing down dt graph. What do you notice about the slope of the dt graph in the slowing down portion of the race? Coming flatter, right? The slope is approaching 0, becoming flatter. So the velocity time graph is approaching 0, going towards 0, because the slope is going towards 0. And it might have a slope here of, we're going to assign it that magical value of -4. My velocity time graph, my velocity is greater than 0. It's above the 0 line, but my acceleration is less than 0. And in fact, what would the acceleration time graph look like? If I were to draw the acceleration time graph in here, it would be like that at -4, wouldn't it? Right? Notice that the signs are opposite here. The velocity is bigger than 0, positive. The acceleration is less than 0, negative. What does that mean for the person running the race? They are slowing down. When the signs are opposite, they are slowing down. When the signs are the same, both positive, they're speeding up. Let's draw slowing down. They've won the race. They're celebrating. Got their hands in the air. Kind of like Ben Johnson crossing the finish line in 1988. You guys, have you ever seen that video? Peyton's asking, is this person slowing down in the positive? Are you asking if they're facing to the right?
Yeah.
Yeah, because here, here's where the origin is, right? So they're traveling in the positive region of displacement, and the velocity is greater than 0. So absolutely, they must be to the right of the origin. Okay, the other way, slowing down negatively. So here's the velocity here. Sorry, the displacement time graph. Again, the slope flattens off, approaches 0. The velocity here gets close to 0, right? If I were to assign it a slope, it might be something like +4. My velocity is less than 0. It's below. My acceleration is positive because of the slope. If I were to draw the acceleration time graph, it would be like this, above, at 4. And in this case here, the person is slowing down to the left. That always makes me think of that because Ben Johnson crossed the finish line with his hand in the air like this. That's why it makes me think of it. I'll have to find it. Okay, I hate to tell you this, but now comes the hard stuff. Okay? Now we're going to go to going from one graph to another. Constructing from one graph to another. You can look at the book if you like. I recommend you just sit and listen to me. Okay. So we're going here from, I guess what I should do is point out page 49, or at least the bottom of page 48 says example 5, converting a dt graph to a vt graph. I'll give you the easy one first. dt to a vt. Okay, they give you some steps. Draw the vt axis beneath the dt graph, that's on page 49, and make the time axis the same as the one on the dt graph. So what they're saying is, we want to take this graph here, this position time graph, and I'm going to redraw for you in red. We want to convert that into a velocity time graph. What they're recommending is that you draw the axis immediately below and use the same time coordinates. Does that make sense, what they're saying? Okay. I find that sometimes that makes things hard. Okay. I've found over the years that it's almost better to draw the graph and then put the axis on after. And it's going to be kind of wonky. Like this might be like 0 to 5, and then suddenly it changes to 17. Like, it's hard to keep it in scale, right? Because it's hard to draw. You almost got to draw it once and then redraw it, okay? I find it's a little easier to do that, but that's me. Okay, so let's look at the DT graph. What's happening in this part of the graph? It's curved, it's curving up. What's happening to the slope? It's going towards 0. Does it ever get to 0? Well, not like right there, it's like that, and then instantly it becomes 0, right? Can we kind of fudge it a little bit, and instead of making it kind of abrupt like that, can we kind of make it more like that, so that it kind of smooths right into 0? Can we assume that it looks like that?
Yeah.
Okay, because otherwise, well, I'll ask you what you think when we're done here. So in other words, the slope here is positive and becomes, I'm going to put double positive there. Here it's positive, and here it becomes 0, right? So the graph of the slope approaches 0. Does that make sense? If you want, you can go back to the previous one here and look for a DT graph similar. This one right here. And the VT graph is just like that, right? Okay. So that's what the VT graph looks like here. DT graph is flat. What does that mean for VT graph? Means 0. From there to there, it's 0. Just like it was here. DT graph is 0. So far, not too bad, right? Okay. What's the slope doing here? Curving down, right? Curving down. The slope is becoming more and more negative, which means the velocity is becoming more and more negative, which means my velocity graph must go down and become more and more negative. How do you know that it's a straight line here? Like, how do you know this is straight and not curved? Well, actually, you're right, Dallas. You'd have to find a bunch of tangent lines and then graph it. It'd be a whole lot of work. Safe to assume for you guys, you're never going to see a velocity time graph that's curved. Okay? Maybe in your futures you might, but for the most part, assume that this is an x squared kind of curve, which makes this an x line and derivative stuff and blah, blah, blah. It's a straight line. What's happening to the slope of the DT graph in this area here? It's maintaining a constant slope, which means my velocity is flat, not straight. And you have to sort of guess at what point it stops being curvy and starts being straight. Okay, so we've created the VT graph from the DT graph, like we said it was.
Wait, so it is DT?
We went from DT, position time graph, to velocity time graph. And to be honest, you probably did a little bit of that in grade 11. Maybe not 4 different ones. You probably just did, here's one, pick which one matches, right? More like this kind of stuff, right? Now it's a matter of sort of putting it all together, which is kind of this next step up. Okay, here's the big daddy of them all. Okay, here is a velocity time graph that we have to now convert to a DT graph. Okay, I need your full attention for about 5 minutes. If you need to sort of stand up, get loose, whatever you need to do, because this is heavy duty here. They've redrawn it here. They've done this kind of thing, right? I'm not a hugest fan of that, but when it's already pre-drawn for me, it helps. Okay. Remember, this is the slope graph of this. This is the slope of the DT graph. This is the slope. This one shows the values of the slope. What is happening to the velocity here? It's not. It's approaching 0, right? The velocity is approaching 0, which means the object is slowing down, which means the slope here must be getting flatter. The velocity here is negative, big negative, double negative. Here it's negative, and then it goes to 0, right? Is it traveling to the right or to the left? The velocity is below, it's negative, so it's traveling to the left. You have to assume that it starts at the origin, right? So I'm traveling to the left, negative, and my slope is approaching 0. If you want to go back to the Ben Johnson pictures, BT graph, which one am I looking for again? I'm looking for that one. So that would be this one right here, right? This one here, DT graph looks like that. Okay. What happens in the next phase? Now the velocity is doing what? Away from 0. Getting faster. But at a constant rate, right? Getting faster at a constant rate. So the velocity is getting bigger in a more positive sense, which means the slope is getting more and more positive, more and more steep. So now is it going turned around and going the other way now?
Yes.
Yes. How do we know? The velocity is above, it's positive. Velocity is above, it's positive. So here the slope must be positive. It's going back towards the origin. You're not going to get that it's going back towards the origin from this, though, right? Because you don't see the origin here. This is not the origin, this is 0. This is 0 meters per second. How do we know, this is the hardest question of the day, how do we know that this blue line here doesn't go all the way to 0? Like, how do we know it stops right there?
Okay.
Not easily, Joey. Was it Joey that said that, or Jake?
Joey.
You're right, Joey. We don't by just sort of, we have to do some calculation. What calculation do we need to do to know that it doesn't go all the way to there? Hard question.
No, you don't.
You only gave me like half a second to pause.
Yeah, but then just let me ask it.
Oh, someone's thinking about it.
What are the price ranges of two triangles?
Yep. Jason's right. It's the area here. The area here is the displacement, right? And the area here is the displacement. If those triangles were equal, right, then it would have gone the same displacement left as it went right. So Jason's right. You'd have to find the area of that one, find the area of that one. And if there's more negative when you're done, well, then it's going to end up here. And if there's more positive when you're done, then it's going to end up here. Does that make sense? I wouldn't expect you to do that. I wouldn't expect you to get this that it's below or above unless I made it blatantly obvious. Like looking at those two, they kind of look the same, don't they? Like they're pretty close, right? For me to be able to deduct a mark or for me to be able to expect you to know that, I would have to make it like something like this. Yeah, one clearly bigger than the other, right? Something like that. That would be unfair for me to make you do that, I think, right? Okay. What's happening to velocity in this region right here? It's constant velocity. Is the object stopped?
No.
No. It's moving forward at a constant speed, which means my line now is straight, not flat, straight. At some point here, it crosses the origin. Can you tell by this where it crosses the origin? The only way would be to calculate a bunch of areas. At this point here, the velocity now starts to decrease and approach 0, which means my velocity time graph has to flatten off. The slope has to flatten off, right? This is a graph of the slope, so it has to flatten off like so. Here the velocity time graph is at 0, meaning that it's moving at a constant speed or stopped? Stopped. Velocity time graph is stopped. Velocity time graph is at 0, so the dt graph is flat. It is stopped. And here the velocity time graph shows that the velocity is increasing in a negative fashion, so it's moving backwards and increasing in speed. If it's increasing in speed, it must be curvy, and it curves down. It increases in slope, like so. That's really hard, Mr. Bennett. I know. It takes practice. It's going to take practice. You're going to make mistakes. I quite often have to come in here and remind myself, I did pretty well today, I didn't, but quite often when I know I'm teaching this lesson, I come in and I make sure I know what I'm talking about before I do this, because I make mistakes. I don't think I made any today. I think I did pretty good.
Great testing things.
You can put anything you want on a cheat sheet, half page.
Wait,
Absolutely. You can cut and paste, but it's got to fit on a half page. I suggest you redraw. It'll stick it in your head a little bit better if you redraw. Jason. I would prefer not, and the only reason of that is because I don't want you selling super duper cheat sheets to everyone and making millions of bucks off it. It could be. Would it make sense for you to buy someone else's cheat sheet? Would it be cost effective? Probably not, right? Because you're not going to know what's on there. You're not going to know how to use it. You're not going to understand it. Probably better to make your own. So that's the only reason that I say no. Okay, I think it's time to do some. Page 71, number 22 to 28. Do you have on your handout there? Do you have those? You do. Oh no, you don't. I have those graphs run off. I'll just have to get them for you.